Hello and welcome. Today we're going to be looking at question number 5 on the AP Chemistry exam 2011 Form B. As always, we're going to be looking through this entire free response question so that you understand how to approach these questions and how to ace the AP Chemistry exam. If you like these videos or find them informative, please be sure to like and subscribe. And with that, let's get started on our question. Here it is. A student is instructed to prepare 100 milliliters of a 1.250 molar sodium hydroxide from a stock solution of 5 molar sodium hydroxide. The student follows the proper safety guidelines, and we're asked to calculate the volume of 5 molar sodium hydroxide needed to accurately prepare 100 milliliters of the 1.250 molar sodium hydroxide. Alright, so this seems like it's going to be a question on dilution. Alright, so let's think about this using the dilution equation. The dilution equation is M1 V1 equals M2 V2. Alright, so here for our initial or our first molarity, we can put the final, which is actually 1.25. And here we have the 100. We're putting this in milliliters since we're also going to get this volume in milliliters. So we really don't care about changing the units back to liters since it's going to be in the same units the whole time. So 125 times 100 is going to be 125. Molarity of the second one is going to be 5. So this volume here is then going to be 125 divided by 5, or 25 milliliters. And that is our answer. Let's move on to the next part. Alright, part B. Describe the steps and a procedure needed to prepare 100 milliliters of 1.250 molar sodium hydroxide solution using 5 molar sodium hydroxide and the equivalent selected from the list below. And we have a balance, a 50 milliliter burette, eyedropper, 25 milliliter Erlenmeyer flask, 100 milliliter Florence flask, drying oven, 100 milliliter graduate cylinder, 25 milliliter pipette, wash bottle of distilled water, 100 milliliter volumetric flask, 100 milliliter beaker, and a crucible. That was a lot of stuff. But let's think about what we can do, what equipment we're going to use, how we're going to go about doing this. All right. So first, we know that we have the 25 milliliters of the 5 molar solution. We know that we need to put that much in there. So let's say first what we're going to do is first we pipette 25 ml of the 5 molar NaOH solution. Alright, that's the first thing we do. And then what do we do? Well, then we need to, then what do we need to do? Well, we need to add the water up to the 100 milliliter mark. So we need to get 75 milliliters of water, but we really don't have somewhere to put that. So what if we just put this water here and put it into the 100 ml volumetric flask? And that way we can then add distilled water up to the calibration mark on the volumetric flask, right? And that would give us 100 milliliters total, or 75 milliliters of the water, right? And that's the second thing we do. And then what? Well, then we need to make sure that it's a uniform solution. So then we stir it using what? We can just we then mix up the solution by vigorously pushing it. Alright, so now this is how we would go about doing this. Now you might have one question, which is that aren't we supposed to add acids to water? Right? So usually when we do this kind of question, we add the water first, then we add the acid. But this, as you can see, is a base. Now this is sodium hydroxide, so it is a strong base. but we have different procedures when we're talking about acids versus bases, right? And even though in case of an acid, we add the water first and then we add the acid, even though the acid in that scenario and this base are going to be around the same strength, we're still allowed to add the base first and then add the water. Because the reason we don't add water to an acid that's already there is because when you're adding that water to the acid, it's going to cause a reaction, and that reaction might release too much heat, and there might not be enough water to like dilute that heat out, so that it doesn't cause something to happen. Bases don't do that big of a release of heat when they react with water, which is why we can add water to a base that's already in the solution. So that is going to be our answer to part B. Let's go to part C. So we have the student is given 50 milliliters of a 1 molar solution of a weak monoprotic acid, HA. The solution is titrated with the 1.250 molar sodium hydroxide to the endpoint. Assume that the endpoint is at the equivalence point. Alright, so the endpoint is at the equivalence point. Then what? Well, let's see. We're going to explain why the solution is basic at the equivalence point of that titration. How are we going to explain that? Well, they asked us to include a chemical equation as part of our explanation, so we're going to make a text box and we're going to start thinking about what we can do right here. So let's add an equation. So we have NaOH plus HA, right? And that becomes H2O plus A minus. And then we really don't need the Na plus, so we can just get rid of that and say OH minus plus HA equals H2O plus A minus, right? And that is going to be our chemical equation. Now we got to think about why it's going to be basic. Let's think about why it's going to be basic. Well, let's see. So we're titrating it with the NaOH to the endpoint, so we're going to have the same amount of HA and OH minus, which means that we're going to end up with just water and the conjugate base of the weak monoprotic acid. Well, what does that mean? At the equivalence point, we simply have the conjugate base of the weak acid HA. Alright, so what does that mean? Since HA is a weak acid, then its conjugate base is a weak base and makes the solution basic. And that's why the pH is going to be greater than 7. That's why the solution is basic at that point. Let's move on to part 2 of part C. Part 2 of part C, here it is. And what do we have here? Identify the indicator in the table below that would be best for the titration. Justify your choice. Well, this is going to be a basic solution, so its pH is going to be greater than 7. So we're going to end up using an indicator that's closest to the pH, the pKa. And that is going to be what? That is going to end up being, it looks like it should be the phenolphthalein. Why does it feel like that should be the phenolphthalein? Because the phenolphthalein has a pKa that is basic, meaning that when we're titrating at the basic range, the indicator is going to be most attuned to that since where the solution is basic. So we are going to use phenolphthalein, and since it has a pKa of greater than 7, so it is going to be most accurate in basic solution, which is in basic solution, and we are in basic solution for this titration. That's it. And we can move on to part D. Move on to part D. Part 1 of part D. So we're told that the student is given another 50 milliliter sample of 1 molar HA. Student adds to the solution that had been titrated to the endpoint in part C. The result is a solution with a pH of 5.0. And question 1 is, what is the value of the acid dissociation constant Ka for the weak acid? Explain the reasoning. Let's think about this for a second. Alright, so let's see. So when we add in another 50 ml of 1 molar HA, we then have the same amount of HA and A minus in solution. I remember we had 50 milliliters and 1 molar of HA to begin with that we titrated, so now we have 50 milliliters of 1 molar of A minus, the conjugate base. So then when we add in another 50 milliliters of 1 molar HA, we're going to end up with 0.5 molar HA and 0.5 molar A minus. So we're going to have the same amount of HA and A minus in solution, the same concentration. So using the buffer equation, we get buffer equation, of course, is the pH equals pKa plus logarithm plus log of concentration of base over concentration of acid. Alright, so that's the buffer equation. Since we found out that the concentration of HA equals the concentration of A minus, right? Then we have that pH equals pKa, right? So since the pH is 5.0, the pKa equals 5.0, and then the acid dissociation constant, or Ka, is going to equal 10 to the negative, so 10 to the negative fifth. And that right there is our answer. Ka equals 10 to the negative fifth. Let's move on to the next part, part 2 of part D. It is so we're going to explain why the addition of a few drops of the sodium hydroxide to the resulting solution does not appreciably change its pH. Alright, let's see what we can do about this question. Well, we have a buffer, right? In solution, we have a buffer at its pKa. Well, what does that mean? That means this is the point where the buffer is strongest, right? Since it has the 1-to-1 ratio of acid and conjugate acid, or base and conjugate base. So adding an acid or base at this point is not going to make a difference, right? Since it's going to only slightly change that ratio of base to acid, which is not really going to do anything. Right? Think about it this way. If we have a 1-to-1 ratio of base to acid, and we turn some of that acid into base, like we have 1-to-1, and now it's going to be 1.1 to 9 to the 0.9, right? Imagining that our base would be 1.1 and our acid would be 0.9. Then if we plug that in, right, we just lost 1/10 of the acid and it became base, but the pH is only changed by 0.087, right, which is not any difference that's going to be noted, even though we just got rid of 10% of the acid. So adding a few drops certainly is not going to change anything. Not going to make a difference in the pH. And that is the answer to that part. Alright, that is it for this question. I hope you enjoyed the video, found it informative. I hope you learned something from it. and be sure to stay tuned for next time when we continue looking at more AP Chemistry FRQs. I'll see you then.